calculate eigenvalues and eigenvectors. And then the third problem is a magnetic resonance problem. So that's the content of the exam.
Magnetic resonance, that was chapter 4, right?
I think so.
Okay.
I think it was 4. I think it was 4 or 5. All right. So what I want to talk about today is we want to continue talking about the Schrödinger equation and how to solve it. Okay, so let's just look at it as a differential equation. So if we write it down, it's IH bar partial with respect to t of psi of x and t is equal to minus h bar squared over 2m times the second partial with respect to x plus v of x. Okay, so that's the Schrödinger equation. We can assume that v is a function of x. There's no time dependence. To the potential. Okay, and so what we want to do now is just solve this thing. Let's look at it as a differential equation and just solve it as we would any differential equation. So one of the primary methods to solving partial differential equations, and more than one variable here, is through a process where we assume that psi of x and t can be written as a function of x only times a function phi, oops, let's use little phi, or let's use capital T, times capital T of t. So this is called separation of variables.
I remember that.
Mm-hmm.
Okay, and so just plug into the Schrödinger equation. So let's just go ahead and plug it into the Schrödinger equation. So first, though, let's note that the partial derivative with respect to t of capital psi, that's just little psi of x and capital T prime of t, where the prime here denotes the derivative. And since t is only a function of time, it's got to be the time derivative. And the partial derivative with respect to x is just psi prime of x t of t. Okay, so then the left-hand side, we can write IH bar, and we have a time derivative. So this is psi of x times capital T prime of t is equal to minus h bar squared over 2m, and then we'll have little psi double prime t of t plus v psi of x and t of t. Okay, and now we can just divide through, let's divide both sides by capital Psi. Then on the left side here, capital Psi is just little psi times capital T. So on the left-hand side, I'll be left with IH bar, capital T prime of T over T. And this has to equal minus H bar squared over 2m times little psi double prime over psi plus v of x. Okay, and so now that since we have, this is a function of x only on the right hand side, and the left hand side is a function of t only. And so if these things are varying, they must be equal to just a constant. I mean, if t is varying and x is varying, and these two sides are equal to each other, they must just be equal to a constant. And so we can call this these must equal a constant, and it's called the separation constant. Call it E. Okay, so then we have two equations. We have one equation for t, so the equation for t is IH bar t prime of t over t is equal to E. And I can solve for t prime. So t prime of t is equal to minus IE over H bar times t of t. So what's the solution to this equation?
Oh, it's an exponential.
Right, it's an exponential. So t of t then is equal to some constant c times e to the minus I e over h bar t. Okay, so the time part of this equation is really simple, or the time part of the solution. The space part is not so simple. So let's look at the space part. That says that minus h bar squared over 2m psi double prime of x, I'm going to multiply through by e, or sorry, by psi, plus v of x psi of x is equal to e psi of x. Okay, so that just set this equal to e, and then multiply through by psi, and you get this equation. So that, now this only depends on x. This is called the time-independent Schrödinger equation. All right, and this, we cannot, we can't solve this time-independent Schrödinger equation without knowing v of x. We need to know what that function is if we're going to calculate it. But we can call we can write the TIFC as minus h bar squared over 2m d2 dx squared plus g of x as an operator operating on psi of x is equal to e times psi of x. And where this operator now is the Hamiltonian. Okay, so we have H.
So that whole thing there in that box is a time independent Schrodinger equation? Sure.
This whole thing is the time independent equation.
Okay.
So H is just a Hamiltonian. That's the Hamiltonian, and you know, so this is the free particle part, if you want to think about that. And then this is the potential that it's in. And so when we write the time independent Schrodinger equation in this form, we can see that this is just an eigenvalue equation. Okay. So now, you know, previously when we were solving these things, H was like a matrix and psi was a column vector. But now psi is a function, a continuous function, and H is this continuous, you know, Hamiltonian. So what we're solving for here are different, you know, functions. So this, you know, when we were solving Hamiltonians also previously for our finite dimensional Hilbert spaces, it was pretty simple. We would have like 3 states or something like that. But now we can have an infinite number of states. So we can have this equation can have an infinite number of solutions. And can have an infinite number of eigenvalues. Okay, so we could have things, you know, we could have E1 and psi1 of x, E2 psi2 of x, E3 psi3 of x, and so on. Okay, but now let's, so suppose so let's just suppose that this is a solution to the problem, okay? So the function is psi and E is the eigenvalue. Then let's calculate the expectation value of the Hamiltonian in the wave function psi. So this is just by definition the integral over dx of psi star of x h psi of x. Okay? And this is just going to be, if h psi equals e psi, this is just e times the integral over dx of psi star of psi, which we're assuming to be 1. Then h squared psi what's the value of h, the expectation value of h squared?
Is it E? Is it
E squared?
E squared.
It's e squared, right, because it's just, I've got two h's, one's gonna hit this and give me e, and the second one's gonna hit it and give me e. Right, so this is just e squared. So that means the variance of h is 0, because this is, the variance is the square root of h squared minus h squared, and that'll just be 0. Okay, so what this is a state of definite energy. This is the stationary state. So for each so if we have a pair EI psi I of x and it satisfies this, then psi I of x and t is just going to be the time part, so we'll have some c e to the minus I e sub I over h bar t times psi little I of x. So we've got this simple time dependence for each piece, but in general, a general wave function psi can be the sum over all these capital psi supplies. Okay, so this is just this is how you write the expansion, in terms of continuous functions rather than the way you did it before, which was in terms of state Kents, in terms of Kents. Okay, and so just let me make a point here that the linear combination of stationary states. Is not stationary. So if we had, if psi 1 was C1 e to the minus I over h bar E1 t times psi 1 of x, and capital psi 2 is C2 e to the minus I over h bar E2t psi 2 of x, then the sum psi total psi 1 plus psi 2 will have, I can't pull out a common exponential here in the energies, and so it won't have a simple time dependence. Okay, so let's look at for a single state. For a single stationary state, we have the psi I star, psi I. So if I just take this thing here and take its conjugate and multiply it by it, well, I'll have, the conjugate's gonna have an e to the plus I in it. And so what I'll have here is the magnitude of C I squared times psi I star psi I. Okay, there's no time dependence here. Okay, but if I look at psi total, and I take its conjugate times itself, then it's gonna be this, we're gonna have kind of a mess here. So we'll have C1 e to the, well, we'll have cross terms. We'll get two things actually. We'll get this term will hit its own conjugates. We'll have mag C1 squared times psi 1 star psi 1 plus mag C2 squared psi 2 star psi 2 plus cross terms that contain e to the minus I over h bar E2 minus E1 times t. Okay, so you'll have a time dependence in here. And so this will not be a stationary state. All right, are there any questions?
So I don't know if that is when we get our interference like before.
That's interference, yeah. Okay, so let's look at the general properties of the Schrödinger equation solution with some potential. So, So the general behavior of the solutions. So let's do this first and then we'll start looking at special cases. So let's write down the time independent part of the equation, so. Time independent equation, minus h bar squared over 2m psi double prime plus v of x psi of x is equal to e psi of x. Okay, and let's just solve for psi double prime. So, let's see, I'll have 2m over h bar squared, and then I'll have, this would be e minus v if I just brought this over, but then this minus sign will flip it, so it should be v minus e. Okay, so this is just writing the equation again. And now we want to look at just two cases to see what the general behavior is, because we have a differential equation here that's really simple. It's just the second derivative of a function equals the function again times something in front of it. Okay, so let's consider a potential. That just, if we draw our coordinate axes, let's just assume it does something like this. We don't have to be more specific than this. Just call that v of x. And then we'll pick a particular energy. So let's just say that, let's try to look at solutions where we have this as the energy. Okay, so in this region, the potential here, in this region, V is greater than E. And then in this region and here, E is greater than V. Okay, and then in this region here again, V is greater than E. Right, and it's just, V here is greater than E. That's it. It's as simple as that. So what do we have then for, if we have psi double prime is equal to minus some number times psi, what kind of solutions are there? Let's say it's minus alpha.
There's the exponential.
Right, what kind of exponential?
It had to have would have to have an imaginary in
Right, exactly.
the argument. Yeah.
So psi of x is equal to some constant times e to the plus or minus I alpha x. Right?
Would it be square root of alpha?
Yeah, I'll just put a square there. Okay, and now what about if we have psi double prime equals plus alpha squared psi?
It's the same thing, but there's no I, the exponential.
Right. Psi of x is equal to c e to the plus or minus alpha x. Okay, so here we have oscillation, and here we have exponential decay. Exponentially increasing is not an option because psi has to be finite. Okay, so what do we have then for our potential then? Let's just draw it again. So if we have if our potential looks something like this, and our energy looks like that. So let's see, if the coefficient is negative, we get oscillation. The coefficient will be negative when what? If E here is greater than V, that's in here. That's when it oscillates. So in here we have oscillation of the wave function. And then when V is greater than E, this thing is positive and we have exponential decay. And so the wave function just does this. So this is psi of x. All right, that's really all there is to it. You can look now at any one-dimensional potential and you know the solution. You know, you don't know it exactly, but you know where it decreases exponentially and you know where it oscillates. Okay, so we could do a more interesting example here where we had a potential that looks like this. Suppose we have an E that looks like that. So you know, here it's exponentially decreasing, here it can oscillate. Here it has to exponentially decrease, but it might reach the end of this, it might reach the other side of this potential and start oscillating again. So that's psi of x, and if this is the potential hump, this is barrier penetration. Or tunneling. Okay, and that's how, you know, alpha decay works in the atom. You have a big alpha particle that it's kind of basically bouncing around, and then that's the potential looks not unlike this, and it actually tunnels out, and that's what gives you alpha decay. Okay, so let's do, we've now come to the infinite square well. Let me make some comments here about the solutions. If you look at the way I drew these things, the way I drew the wave function, not only is the wave function itself continuous, so it's continuous across changes, you know, at boundaries.
I guess it would have to be if you're differentiating it, right?
So the function itself is continuous across the boundary, but also the slope, so the derivative of the function is continuous across the boundary. Unless the potential makes infinite jumps. Okay, so you can always draw a nice continuous wave function there, unless the potential makes an infinite jump. So of course, the first problem that we'll do, we'll have a potential that makes an infinite jump. So this is the infinite square well in one dimension. Okay, so for this particular problem, we do have a potential that goes to infinity. have the length of the well is A, and V of X is equal to 0, inside the well. And V equals infinity outside. Okay, so here the derivative of the wave function doesn't have to be continuous. So, but the wave function still does. So let's go ahead and first of all, we know it has to wave. It has to wave inside here because any energy that we have that's above 0, the potential is 0, so we have to have some kind of waving inside the box. Okay? But I can have there's no probability for finding a particle outside because the potential is infinite. So whatever we draw in the box has to go to 0 at the edges of the box. Okay, so that's the general solution. Let's work it out for this particular case. So write down the equation. So this is the time-independent Schrödinger equation. So it will be minus h bar squared over 2m psi double prime of x. Now, the potential is 0, so v is 0, and it's just equal to e psi of x. So this is, let's call this region 1, region 2, and region 3. So we're going to do several different variants of this, so that's why I'm labeling these regions. So we'll do the finite square well next. Okay, so in region 2, this is the Schrödinger equation. And so psi 2 double prime is minus 2m e over h bar squared psi 2. All right, and let's call this let k squared be 2me over h bar squared. All right, so now we just have a really simple equation. Psi 2 double prime is equal to minus k squared psi 2.
And then we'd use our solution from up there, right? This side, then psi is equal to.
Right. We know it oscillates. So let's write psi 2 of x is equal to a sine kx plus b cosine kx, same thing as exponentials. All right, now we have just, this is a differential equation and we have to solve it by satisfying boundary conditions. So we must satisfy the boundary conditions. So that means that psi 2 at 0 has to equal psi 2 at A. Those both have to equal 0. Okay, so if we take psi 2 at 0, that will be A times 0 plus B. Cosine of 0 is 1. And this equals 0. So we don't get any information from A here because we multiplied it by 0. But B, that just means B equals 0. So we do find that there's no cosine component here. We can just write the solution in terms of, so we have psi 2 of x is equal to A sine kx. Okay, and now we have to satisfy the boundary, the only other boundary condition that we have is that psi 2 at A equals 0 this implies that we have a sine ka equals 0. Okay, so what does that mean for k?
It has to be the integer multiple of pi.
Right. So ka has to be an integer multiple of pi, and so we have psi 2 of x is equal to a times sine n pi x over a. Okay, so this means that k, we can put a little subscript n on it, is equal to n pi over a. Okay, so now let's see what we can already do something with this. We already said that k squared was 2m e h bar squared. So 2m e over h bar squared, so we can square this. That's n squared pi squared over a squared is equal to 2m e over h bar squared. So that means e, which is now depending on n, is n squared pi squared h bar squared over 2n a squared. Okay, so we found the energies. Okay, so this is for n equals 1, 2, 3, and so on. So there's an infinite number of states. And that's, that's energy quantization comes from the boundary conditions. Okay, so that's pretty remarkable. That's how particles behave in boxes. Now let's normalize this thing. So let's normalize it. We have to have the integral over dx. Now we're only integrating from 0 up to a of psi star x psi, and we want this thing to be 1. Right, so this will be a star a times the integral over dx, and now we'll have sine squared of n pi over a times x. Okay, and this all has to equal 1. All right, so let's see, this is mag a squared, and I'll just change variables here. So we can call this, let's let y equal n pi over a x. So dy is equal to n pi over a dx. And then we have, we've got mag a squared. Let's see, if I solve for dx, I'll have an a over n pi, and then I'll have an integral from 0 to infinity dy of sine squared y, and all of that has to equal 1. Oh, sorry, what am I doing? What infinity here? This is a.
Where'd the sine squared come from?
Psi star sine.
Oh, right, okay.
All right, so how do you do this integral?
That's integration by parts, right?
Just use a trig substitution.
Or we can do that.
Yeah, what is it,
Cosine squared plus one.
or minus?
This is 1/2, 1 minus cosine 2y.
I have to look at the table every time.
I forgot about that one.
Okay, well. Anyway, so this becomes easy because this thing integrates to, oh wait, let's see, sorry. If this integration is up to a, then if x is equal to a, this is n pi. Sorry, for the dy integration, that's n pi. So this thing is just gonna integrate to a sine, and then there'll be some multiple of n pi and 0, so this thing, that term just goes away. So it's just 1/2 times n pi. So we have mag a squared a over n pi is times 1/2 n pi equals 1. So the n pi's go away, and a is equal to the square root of 2 over a. Okay, so let's write down what we know so far. So for the square well, we have the basis functions are, let's label them with an n now. These are the normalized basis functions. 2 over a times the sine of n pi x over a. Okay, so we know the basis functions, and we also know the energies. It's n squared pi squared h bar squared over 2m a squared. All right, so let's draw some of the base states and
I'm pretty sure I did this exact same problem in PDE.
you should have done it in modern physics, but
I probably did it there too.
yeah.
It might be wrong number instead.
Yeah, we did the infinite square well stuff, and I remember because I hated it.
What's that?
I said, I remember doing the infinite square well stuff in modern physics because I hated it.
Well,
That's okay, it's okay.
hope you're liking it better now.
Yeah, well, yeah.
All right, so let's draw some of the first few base states. So let's look at n equals 1. So for n equals 1, psi 1 of x is 2 over a. It's just going to be sine pi x over a. Okay, so when x is 0, it's 0, and then when x is a, it's sine of pi, which is 0. So it just looks like this. Okay, and if we were to draw it outside the well, this is where I mentioned before, because the well is infinite, the derivative here is not continuous. Right, the derivative here is negative on the left there, and then the derivative here is 0, so it's discontinuous.
So,
But that's only because there's an infinite well.
so for every number n, we're just gonna go like a different harmonic in the box.
Yeah, basically. So that's n equals 1, and for n equals 2, psi 2 goes like sine 2 pi x over a. So that means when x goes from 0 to a, sine goes from 0 to 2 pi, so we'll get a full wave inside the well.
I remember this.
So now we'll get this, and then of course it's 0 outside the well. Okay. And then we'll do n equals 3. Then psi 3 is like sine 3 pi x over a. So it's going to have another node in the box. So this is a node. So here we have 2 nodes. Okay, so the general principle here is there's no nodes up in this box. So as you increase n, you add nodes into the box. It just increases the number of nodes in the box. And the energy goes up as n squared. En goes as n squared, so this goes up fast.
So what is this space under the line? Like the negative part of that?
It's just the amplitude.
Okay, so,
Yeah, so if we,
Right, when we take the square of it, it'll.
so,
oh,
yeah,
okay.
this is all just psi of x. So if we square it, well, let me show you how the energy goes up. So we can look at En plus 1 minus E sub n and see the difference between states. So we'll have this overall factor of 8 pi squared h bar squared over 2ma squared come out there. And then we'll have n plus 1 squared minus n squared. I'm just plugging in n plus 1. So this is n squared plus 2n plus 1 minus n squared. So delta n, the difference between En plus 1 and En, is 2n plus 1 times the prefactor. Okay, so that means this thing goes up, it goes up twice every, 2n plus 1 increases rapidly with n. So the energy levels get further and further and further apart. Right? So it just gets, all right, and then so the probability of finding the particle you can draw that. So for n equals 1, now the wave function has to go, the square of the wave function here will look something like this. So if you have n equals 1, the probability to find it is mostly just underneath the, right in the middle of the box. And then for n equals 2, it has to go smoothly to 0 at the middle.
Okay, there, that's what I remember.
Right? So there's no probability of finding it in the middle of the box. And then for n equals 3, looks like that. Okay, so you can have mixtures of these things, which is what the interesting part is. And so now that we can put it all together, let's see what is the most general wave function for a particle in a one-dimensional box. Well, if we write the most general wave function, it has to be a sum over I now of the Ci times e to the minus I over h bar. I guess we can use n here, so it's, since we've been using n, t psi n of x. Okay, so if I wanted to have a linear combination of states here that was not stationary, so if we plug in for all of our numbers here, this would be n squared, pi squared, let's see, the h bar would go away, right? So, it would be one h bar upstairs over 2m a squared times the square root of 2 over a times the sine of n pi x over a. Okay, so that would be a general wave function. Okay, are there any questions about, are there any questions about it so far?
I guess I kind of have a question, but
Yeah, what's that?
so if it has no probability of being in this middle, like, would it be able to move, or would it be able to go between those two nodes? Because otherwise it wouldn't be there. Like, I think that's interesting, that like, if you have a box and it's a certain energy, it just won't be at specific locations. Not really much of a question, but.
Yeah, no, that's a good question. But so the probability won't change. So if it's, I mean, number one, you can't say that it's moving back and forth between them, right?
Yeah.
This itself is a stationary state,
Oh, okay.
right? It's a standing wave in the box.
Oh, I see. Okay.
So it's not any different than just having, a sound wave in a room, like a big, bass sound wave or something. You could stand at a node and you wouldn't hear anything.
Yeah. Okay. Makes sense.
Right. So it's like that.
You ever actually do that before? Like if you're in a room of a certain shape, you can stand in certain places, you just don't hear anything.
Yeah, there's places like that.
Yeah, it's not a fun experience. It really
I
is.
want to so bad. That sounds like cool.
In Congress, what is the big rotunda room, whatever it's called?
Oh man.
Yeah, there's a place where you can stand where you can like hear everybody on the other side, like it focuses the sound at one
Yeah.
location and stuff.
It's freaky when it happens to you. And you don't know that was going to happen to you. Like you just go walk into a certain part of a room and then suddenly you're deaf.
That'd be interesting. Could be aliens. All right, so let's all right, this seems like just a kind of, the one-dimensional particle in a box seems like it's just kind of a throwaway physics problem or something, but it actually is really useful. It has real utility, and I'll explain why in just a minute. But let's calculate for this one-dimensional box the energy eigenvalues for a box that is of width 3 angstroms. Okay, so if we do that, and we'll calculate them in electron volts. So 1 eV, to remind you, is 1.602 times 10 to the minus 19 joules. So E1 will be 4.18 electron volts. E2 will be 16.73 electron volts, and E3 will be 37.6 eV. Okay, so you can see that it more than doubles each time you go up in But where this actually, where you can actually observe this is, in a three-dimensional particle in a box. Um, let's see. You can calculate this for a three-dimensional particle in a box for, so sodium chloride is a cubic structure. This is a cubic material, and we can draw the structure of the cube. So this dimension of the cube is about 5.63 angstroms, so it's, you know, just a little bit bigger than the example we gave over here. But here we can put chlorine atoms on the corners. And then we can put sodium atoms that are on the edges, and they're also on the faces. Chlorine's on the face. Okay, so inside the box, if you were to draw, you can draw this this little shape in here is this is an octahedral site. And at the center of the box, you know, you could, if there's an atom that's missing, so this is sodium chloride as a salt can be looked at as sodium plus chlorine minus. And so what you can do is you can do things like pop out a chlorine atom and put in an electron, and it will be happy inside there because it's just a negative charge. And it's like an electron in a three-dimensional box. Okay, so it's very similar to this. And you can calculate the wavelength of, you can calculate the excited states of the electron in that box, and it closely matches what you calculate just from using a particle in a three-dimensional box.
That's pretty cool.
Okay, so what's remarkable about that is that the box doesn't look anything like the infinite dimensional particle in a box, right? So the fact that it gets anywhere close to the, you know, correct behavior, that means in physics that you've basically solved the problem.
So is there like a minimum, like a minimum height of that potential, where it's still
Effectively.
It's effectively infinite?
Yeah.
Yeah, I guess for something as small as an electron, it doesn't take a lot for something to be effectively infinite.
Yeah, I mean, it's pretty crazy because the wave function of the electron is actually doesn't really look very much at all like any of these.
Right.
Right, so the wave function can vary quite a bit and still have roughly the same energies. So these things are called color centers.
It's also interesting because that equation up there, it looks like it's like the energy levels are completely independent of any properties besides like the size of the box and mass.
Right, yeah, that's the case for infinite square one.
Okay.
Yeah.
So like if like hypothetically you had a particle in there instead of electrons that had like a negative 2 charge, it would still function exactly the same.
Yeah, except the potential would be.
Oh, the potential itself would just be different.
I mean, it'd be a
Right.
factor of 2, but that would be it.
Right, that makes sense.
So it is remarkable, it really is, I mean, it's a stunning, you know, the fact that this thing, with the way they do it is they look at you can shine light on these things and excite the atoms inside there, and then,
So you could just
you,
you could just take a block of salt and then just kind of pull a chloride out of there.
you would just heat it, and you would take like sodium chloride,
Right.
just salt, table salt, and sodium metal, and just drop the sodium chloride in the sodium metal, and just heat it,
Oh, okay.
so that you're chlorine deficient,
I see.
and then you'll end up with these color centers inside.
Okay, so where do I guess you have to like put some free electrons in there somehow?
No, they'll come from, you know, wherever.
Just ambiently from wherever.
Yeah,
Okay.
because it's energetically favorable. I mean, the Earth, you know, is like this big sink, right?
Right.
So
Okay.
charge will balance out. But so with that, you know, what you're doing is you're providing a thermodynamic driving force for the sodium atoms to go into the sodium chloride lattice,
Right.
right? Because they can go. There's in any crystal there is always some quantity of defects and vacancies because of thermodynamics.
Okay.
And so the sodium, if those vacancies are there, and they're always there, then the sodium has a big thermodynamic driving force to go in and try to fill those vacancies.
So in my little box of Morton salt in my cabinet,
Yeah.
there's a chance that one of those has a particle in the box.
Oh, sure, yeah, they're in there.
Oh, nice.
There's not high enough density for you to see them.
Okay.
But if you take, in some of these crystals that are like clear like that, you know, it'll change their color because you'll actually see them. That's why they call them color centers. So,
Oh, okay.
you know, it'll turn it like purple or, you know.
Is that what pink
Because
is?
it-
Himalayan pink salt is?
Because it's big, so because it's missing,
Probably, actually, yeah, it probably is. It's probably some kind of color center in there.
so because it's
But
missing,
it could be also a different mineral, like so you might have.
I think it's iron, right? Is that why it's pink?
Oh, probably.
Well, I mean, so if you've got if you've got a heavier mineral in there, something like iron, something that can donate electrons.
Yeah.
Then that's probably what it's doing, though. It'll donate those electrons to the color center.
Oh,
Turn
I
it
see.
pink or something like that.
I see.
You know, so it'll donate those electrons to the vacancy or something like that. I mean, there's so many ways to change the color of a crystal like that.
Okay. That's pretty interesting.
Yeah, it's due to trace minerals.
Right. But the
Yeah,
trace
but
minerals
but-
themselves
but-
are,
But, you know, what's the more detailed explanation?
the trace minerals are
What are the
donating
trace minerals doing
electrons. Okay.
that make it pink? No. It's not like Prussian blue or something weird like that. You know? It's gotta be something simple because my guess is it just donates electrons to the color center or something.
Mhm.
Okay, so, yeah, that's all, unless there's any other questions.